Hey guys, welcome back to my channel. And in today's video, we'll be talking about theory of computation from an research paper. The topic where the name is fundamentals of the theory of computation. We'll be seeing about all the things that this research paper had. And since we have extracted all the contents from the research paper, we'll see about all the fundamental concepts and algorithmic computations from formal languages to grammars to computational complexity and also intercaptable problems. And this text explores about the core principle field where the theory of computation is used in computer science. By connecting this theory to practical applications, this author aimed to equip the students all the essential tools and techniques for designing and analyzing the algorithms. So, without wasting any time, let's get started. So, firstly, the languages and the problems. The languages which are there are the symbols, alphabets, and strings. Which are the building block of formal languages, including the concepts of symbols, alphabets, and strings. The second one is the language operation, which are the fundamental operation performing union, intersection, and complementations in the TOC. Then we have problem representation, which are the different ways in which the computational problems can be cast as formal languages. And then including we can have decision problem, and we can also optimize these problems by solving them. Let's go to the next topic, which is the regular expressions and the languages. So, about the regular languages and construction, these are the classes of regular language and the operations which can construct them, such as concatenation in the sense merging two things, and then we have clean star and also union. And then we have regular expressions where the formal notation uses to represent the regular language and the equivalency between the regular expression and the finite automata. The third thing which we have is application of regular expressions, where the widespread use of these regular expression is done in text processing and also for pattern matching and designing the programs in different languages. Then we have machine finite automata, where the basic things happen in finite automata is the about the basic machine notation, which consists of all the fundamental concepts of machines and also includes the states and transition where it happens, and it's also acceptance of strings. Then we have deterministic finite automata, which is also the simple form of finite automata where each state has a unique transition for each input symbols. Then we have non-deterministic finite automata, which is like more of finite automata. The state have multiple transition for a single output. So this was about uh, machines, different type of finite automata. Now, coming to the properties of these finite state languages, we have the closure property, the pumping lemma property, and then applications of this pumping lemma property. When it comes to closure property, the closure of regular languages, which are under various operations such as union, intersection, and also complementation. And in pumping lemma, it is used for proving certain languages which are not regular. And by showing this, they do not satisfy the pumping property. This is where we use the pumping lemma. And then coming to applications of these pumping lemma, they are used for demonstrating the languages like palindrome and direct language are not regular. Now moving to the next slide, we have machines too, the stacks and tapes. which are the push-down automata. In this model of computation, that extends the finite automata with a stack, and it allows the recognition of context-free languages. Then we have turning machines, where the most general model of computation with a bound tape and a finite state control. And these are capable of recognizing all the computable languages. Then we also have undecidable languages, which the languages which cannot be recognized by any turning machines, such as halting problem or even demonstrating the limitations of these computation in the machines. This is how the stacks and tapes work in the machines. Then we have grammars, which are really important in computing, which is the text context-free grammar, which is a formal system for generating context-free languages with production rules that can introduce non-terminal symbols also. Then we have parsing with PDA. This is used for pushing down the automata to recognize and also parsing the strings generated by context-free grammars. Then we have non-text-free languages, where the languages cannot be generated by any context-free grammar, and also such languages need to be balanced, need to have balanced parentheses. Now, talking about computational complexity, we have four types, which is polynomial time, P completeness theory, the non-deterministic polynomial time, and NP completeness theory. We learned all about this even in our um, uh, even in our data structure and also ADA. So polynomial time is the class of problems that can be solved efficiently by deterministic turning machines, which are known as complexity classes of P. Uh, then we have P completeness theory, where they identify the problems which are hardest in the P class, and then the study of reduction between these problems. And then they reduce these problems from the class P. Then we have non-deterministic polynomial time. Here the classes of problems can be verified efficiently by non-deterministic by turning machines, which is known as complexity classes NP. Then we have NP completeness theory, where they identify the hardest problem from the NP class. In P completeness theory, they identify the classes hardest from the P classes, whereas here in NP completeness theory, they identify from the NP class. And then they study how to reduce this problem. And that's how now, next one is feasible and intractable problems. First one is the polynomial time. The polynomial time problems can be solved efficiently by deterministic algorithms, such as finding the shortest path in the groove, like uh, the Dijkstra's or Prim's, etc. Then we have non-deterministic polynomial time, where the problem of each solution can be verified efficiently and which may be hard to find. And such as these problems also includes traveling salesman problem. Then we have P complete problems, the hardest problems within the class P, which are believed to be inherently sequence and also difficult to parallelize. And lastly, we have NP complete problems, the hardest problems within the class NP, which are also believed to be intractable and not solvable in polynomial time. And that's it for today's video. Thank you for watching.